Is there a problem that just haunts you? It sits there in the dark corners, twin prime conjecture, Riemann hypothesis, Goldbach conjecture.
Twin prime, that sounds... Well, again, so I mean, the problems like the Riemann hypothesis, those are so far out of reach.
You think so?
Yeah, there's no even viable strategy. Like, even if I activate all the cheats that I know of in this problem, like there's just still no way to get from A to B.
Yeah.
I think it needs a breakthrough in another area of mathematics to happen first, and for someone to recognize that that would be a useful thing to transport into this problem.
So we should maybe step back for a little bit and just talk about prime numbers.
Okay.
So they're often referred to as the atoms of mathematics. Can you just speak to the structure that these atoms provide?
So the natural numbers have two basic operations attached to them: addition and multiplication. So if you want to generate the natural numbers, you can do one of two things. You can just start with 1 and add 1 to itself over and over again, and that generates you the natural numbers. So additively, they're very easy to generate: 1, 2, 3, 4, 5. Or you can take the prime number. If you want to generate multiplicatively, you can take all the prime numbers, 2, 3, 5, 7, and multiply them all together. And together, that gives you all the natural numbers, except maybe for 1. So there are these two separate ways of thinking about the natural numbers from an additive point of view and a multiplicative point of view. And separately, they're not so bad. So like any question about that natural numbers that only was addition is relatively easy to solve. And any question that only was multiplication is relatively easy to solve. But what has been frustrating is that you combine the two together, and suddenly you get this extremely rich... I mean, we know that there are statements in number theory that are actually as undecidable. There are certain polynomials in some number of variables. Is there a solution in the natural numbers? And the answer depends on an undecidable statement, like whether the axioms of mathematics are consistent or not. But even the simplest problems that combine something multiplicative, such as the primes, with something additive, such as shifting by 2, separately we understand both of them well. But if you ask, when you shift the prime by 2, how often can you get another prime? It's been amazingly hard to relate the two.
And we should say that the twin prime conjecture is just that. It posits that there are infinitely many pairs of prime numbers that differ by 2.
Yes.
Now, the interesting thing is that you have been very successful at pushing forward the field in answering these complicated questions of this variety. Like you mentioned, the Green-Tao theorem. It proves that prime numbers contain arithmetic progressions of any length.
Right.
Which is mind-blowing that you could prove something like that.
Right. Yeah, so what we've realized because of this type of research is that there's different patterns have different levels of indestructibility. So what makes the twin prime problem hard is that if you take all the primes in the world, 3, 5, 7, 11, so forth, there are some twins in there. 11 and 13 is a twin prime, pair of twin primes and so forth. But you could easily, if you wanted to, redact the primes to get rid of the these twins. Like the twins, they show up, and there are infinitely many of them, but they're actually reasonably sparse. There's not. I mean, initially there's quite a few, but once you got to the millions, the trillions, they become rarer and rarer. And you could actually just, like if someone was given access to the database of primes, you just edit out a few primes here and there, they could make the twin prime conjecture false by just removing like 0.01% of the primes or something. Just well chosen to do this. And so you could present a censored database of the primes, which passes all of the statistical tests of the primes. That it obeys things like the prime number theorem and other facts about the primes, but doesn't contain any twin primes anymore. And this is a real obstacle for the twin prime conjecture. It means that any proof strategy to actually find twin primes in the actual primes must fail when applied to these slightly edited primes. And so it must use some very subtle, delicate feature of the primes that you can't just get from like aggregate statistical analysis.
Okay, so that's out.
Yeah. On the other hand, arithmetic progressions has turned out to be much more robust. Like you can take the primes and you can eliminate 99% of the primes, actually. And you can take any 99% you want. And it turns out, and another thing we proved is that you still get arithmetic progressions. Arithmetic progressions are much, they're like cockroaches.
Of arbitrary length.
Yes.
Though.
Yes.
That's crazy. I mean, so this, for people who don't know, arithmetic progressions is a sequence of numbers that differ by some fixed amount.
Yeah. But it's again like it's an infinite monkey type phenomenon. For any fixed length of your set, you don't get arbitrary length progressions. You only get quite short progressions.
But you're saying twin prime is not an infinite monkey phenomena. I mean, it's
No,
a very subtle monkey. It's still an infinite monkey phenomenon.
right? Yeah. If the primes were really genuinely random, if the primes were generated by monkeys, then yes, in fact, the infinite monkey theorem would.
Oh, but you're saying that twin prime you can't use the same tools. Like it doesn't appear random almost.
Well, we don't know. We believe the primes behave like a random set. And so the reason why we care about the twin prime conjecture is a test case for whether we can genuinely confidently say with 0% chance of error that the primes behave like a random set. Okay, random versions of the primes we know contain twins, at least with 100% probability, or probably tending to 100% as you go out further and further. So the primes we believe that they're random. The reason why arithmetic progressions are indestructible is that regardless of whether your set looks random or looks structured, like periodic, in both cases, arithmetic progressions appear, but for different reasons. And this is basically all the ways in which there are many proofs of these sort of arithmetic progression type theorems, and they're all proven by some sort of dichotomy where your set is either structured or random, and in both cases, you can say something, and then you put the two together. But in twin primes, if the primes are random, then you're happy, you win. But if the primes are structured, they could be structured in a specific way that eliminates the twins. And we can't rule out that one conspiracy.
And yet you were able to make as I understand, progress on the K-tuple version.
Right, yeah. So the one funny thing about conspiracies is that any one conspiracy theory is really hard to disprove. That if you believe the world is run by lizards, you say here's some evidence that it's not run by lizards. Well, that evidence was planted by the lizards.
Yeah,
right. You may have encountered this kind of phenomenon. Yeah. So,
yes.
so a pure there's almost no way to definitively rule out a conspiracy, and the same is true in mathematics. That a conspiracy is solely devoted to eliminating twin primes. You have to also infiltrate other areas of mathematics to sort of, but it could be made consistent, at least as far as we know. But there's a weird phenomenon that you can make one conspiracy rule out other conspiracies. So if the world is run by lizards, it can't also be run by aliens.
Right.
So one unreasonable thing is hard to disprove, but more than one, there are tools. So for example, we know there's infinitely many primes that are no two of which are so the infinite pairs of primes which differ by at most 246 actually is the current record.
Oh, so there's like a bound.
Yes.
On the
right. So there's twin primes. There's this thing called cousin primes that differ by 4. There's thing called sexy primes that differ by 6.
What are sexy primes?
Primes that differ by 6. The name is much less. The concept is much less exciting than the name suggests.
Got it.
Okay. So you can make a conspiracy rule out one of these, but once you have 50 of them, it turns out that you can't rule out all of them at once. It requires too much energy somehow in this conspiracy space.
How do you do the bound part? How do you develop a bound for the difference between the primes that?
Okay, so
that there's an infinite number of.
So it's ultimately based on what's called the pigeonhole principle. So the pigeonhole principle is a statement that if you have a number of pigeons and they all have to go into pigeonholes, and you have more pigeons than pigeonholes, then one of the pigeonholes has to have at least 2 pigeons in it. So there has to be 2 pigeons that are close together. So for instance, if you have 100 numbers and they all range from 1 to 1,000, 2 of them have to be at most 10 apart. Mm-hmm. Because you can divide up the numbers from 1 to 100 into 100 pigeon holes. Let's say if you have 101 numbers. If you have 101 numbers, then 2 of them have to be distance less than 10 apart, because 2 of them have to belong to the same pigeonhole. So it's a basic feature of a basic principle in mathematics. So it doesn't quite work with the primes directly, because the primes get sparser and sparser as you go out. That fewer and fewer numbers are prime. But it turns out that there's a way to assign weights to numbers. So there are numbers that are kind of almost prime, but they're not. They don't have no factors at all other than themselves and 1, but they have very few factors. And it turns out that we understand almost primes a lot better than we understand primes. And so, for example, it was known for a long time that there were twin almost primes. This has been worked out. So almost primes are something we can't understand. So you can actually restrict attention to a suitable set of almost primes. And whereas the primes are very sparse overall, relative to the almost primes, they actually are much less sparse. They may you can set up a set of almost primes where the primes have density like say 1%. And that gives you a shot at proving by applying some sort of original principle that there's pairs of primes that are just only 100 apart. But in order to prove the twin prime conjecture, you need to get the density of primes inside the almost primes up to a threshold of 50%. Once you get up to 50%, you would get twin primes. But unfortunately, there are barriers. We know that no matter what kind of good set of almost primes you pick, the density of primes can never get above 50%. It's called the parity barrier. And I would love to find, so one of my long-term dreams is to find a way to breach that barrier, because it would open up not only the twin prime conjecture, but the go-back conjecture, and many other problems in number theory are currently blocked because our current techniques would require going beyond this theoretical parity barrier. It's like going faster than the speed of light.
Yeah, so we should say twin prime conjecture, one of the biggest problems in the history of mathematics. Go-back conjecture also. They feel like next door neighbors. Has there been days when you felt you saw the path?
Oh yeah, sometimes you try something and it works super well. You again the sense of mathematical smell we talked about earlier. You learn from experience when things are going too well,
Yeah.
because there are certain difficulties that you sort of have to encounter. I think the way a colleague might put it is that like if you are on the streets of New York and you put in a blindfold and you put in a car and after some hours the blindfold is off and you're in Beijing. I mean, that was too easy somehow. Like there was no ocean being crossed. Even if you don't know exactly what was done, you're suspecting that something wasn't right.
But is that still in the back of your head? Do you return to the prime? Do you return to the prime numbers every once in a while to see?
Yeah, when I have nothing better to do, which is less and less times, which is I get busy with so many things these days. But yeah, when I have free time and I'm too frustrated to work on my sort of real research projects, and I also don't want to do my administrative stuff, or I don't want to do some errand for my family. I can play with these things for fun, and usually you get nowhere. Yeah, you have to learn to just say, okay, fine. Once again, nothing happened. I will move on. Yeah, very occasionally one of these problems I actually solved. Well, sometimes, as you say, you think you solved it, and then you're euphoric for maybe 15 minutes, and then you think I should check this because this is too easy, too good to be true, and it usually is.
What's your gut say about when these problems would be solved? Twin prime and go-back.
Prime, I think we'll
10 years?
keep getting more partial results. It does need at least one. This parity barrier is the biggest remaining obstacle. There are simpler versions of the conjecture where we are getting really close. So I think in 10 years, we will have many more, much closer results. We may not have the whole thing. So twin primes is somewhat close. Riemann hypothesis, I have I mean, it has to happen by accident, I think.
So the Riemann hypothesis is a kind of more general conjecture about the distribution of prime numbers, right?
Right. Yeah. It states that sort of viewed multiplicatively, like for questions only involving multiplication, no addition, the primes really do behave as randomly as you could hope. So there's a phenomenon in probability called square root cancellation that, like if you want to poll, say, America on some issue, and you ask one or two voters, and you may have sampled a bad sample, and then you get a really imprecise measurement of the full average. But if you sample more and more people, the accuracy gets better and better, and the accuracy improves like the square root of the number of people you sample. So yeah, if you sample 1,000 people, you can get like a 2-3% margin of error. So in the same sense, if you measure the primes in a certain multiplicative sense, there's a certain type of statistic you can measure, and it's called the Riemann zeta function, and it fluctuates up and down. But in some sense, as you keep averaging more and more, if you sample more and more, the fluctuation should go down as if they were random. And there's a very precise way to quantify that, and the Riemann hypothesis is a very elegant way that captures this. But as with many other areas in mathematics, we have very few tools to show that something really genuinely behaves like really random. And this is actually not just a little bit random, but it's asking that it behaves as random as an actually random set, this square root cancellation. And we know, actually, because of things related to the parity problem, actually, that most of our usual techniques cannot hope to settle this question. The proof has to come out of left field. But what that is, no one has any serious proposal. And there's various ways to sort of, as I said, you can modify the primes a little bit, and you can destroy the Riemann hypothesis. So like it has to be very delicate. You can't apply something that has huge margins of error. It has to just barely work. And like there's like all these pitfalls that you have to like dodge very adeptly.
The prime numbers is just fascinating.
Yeah.
What to you is most mysterious about the prime numbers?
So that's a good question. So, like conjecturally, we have a good model of them. I mean, like as I said, I mean, they have certain patterns. Like the primes are usually odd, for instance. But apart from these sort of obvious patterns, they behave very randomly. And just assuming that they behave, so there's something called the Kramer random model of the primes. That after a certain point, primes just behave like a random set. And there's various slight modifications to this model, but this has been a very good model. It matches the numerics. It tells us what to predict. Like I can tell you with complete certainty the twin prime conjecture is true. The random model gives overwhelming odds it is true. I just can't prove it. Most of our mathematics is optimized for solving things with patterns in them. And the primes have this anti-pattern, as do almost everything, really. But we can't prove that. Yeah, I guess it's not mysterious that the primes be it's kind of random because there's sort of no reason for them to be um, to have any kind of secret pattern. But what is mysterious is what is the mechanism that really forces the randomness to happen. And this is just absent.